Hi, today we're going to talk about a problem to do with the black body spectrum. This will be a question from the WJEC's PH2 2015 paper, but a lot of these black body spectrum questions are exactly the same, so, well, similar anyway. So the things you're going to need for this are two laws: Stefan's law, which is luminosity, and there's the Boltzmann's constant, and the temperature. Okay, and also you'll need Wien's law, max, Wien's constant, and the temperature. So, the first question, you're given a cell called Aldebaran, and it has the following data that they give you. So it's always a good idea to take note of every bit of data they give you. So first of all, the radius of Aldebaran is 44.2 times larger than the radius of the Sun. And they give you the luminosity, which is 518 times more luminous than the Sun. So they also give you the radius and the luminosity of the Sun. So this is important to have as well, because you write that down. The Sun is 6.96 times 10 to the 8 meters. And the luminosity is 3.85 10 to the 1026 watts. Right. So the first thing they want you to do is use Stefan's law to calculate the surface temperature, a value for the surface temperature of Aldebaran. So first thing you need to do is convert these into SI units. So obviously, first RA, you multiply it by the radius of the Sun, and you get out 3.08 times 10 to the 10 meters. It does say 3.07 in the mark scheme, but I think it's a rounding error there, but it doesn't matter. They'll give you the right mark anyway if you put the numbers in correctly. So now you want to do it is rearrange Stefan's law for t. So first of all, we'll put it for t to the power of 4, which is L over sigma 4 pi r squared. So now we've got to take a fourth root, just remember that. You could lose a mark for not doing this bit. Here you go. Right, then we plug the numbers in, and that's, oh yeah, it would help if I need to also calculate the luminosity of Aldebaran, so quickly do that. 3.85 times 10 to the 26. So you get out about 1.99 times 10 to the 29 watts. Right, so you plug these in. 29. Oh yeah, and also the Stefan Boltzmann constant is this, the value of 5.67 times 10 to the minus 8 watts meters per meter squared per Kelvin per 4. So over 5.67 times 10 to the minus 8 times 4 pi times 3.08 times 10 to the 10 squared. And you get out 4,142 Kelvin for this. In the mark scheme, if you used 3.07 times 10 to the 10, so times 10 to the 10 as your radius for the luminosity of the Sun, then, no, for the radius of the Sun, no. For your radius of Aldebaran, I'm sorry, then you'd get 4,150. So, but they shouldn't, being 8 Kelvin off that, you shouldn't get as a mark. Also, they said you would get, this is made out of 4 marks, and they said if you calculated for the Sun inside the temperature of the Sun, so that's about 5,865 Kelvin, then you'd only get 3 marks because you didn't use the numbers for Aldebaran, but you did work out the Stefan's law. My next one, I'll quickly need to draw a quick graph, because you have a graph of the continuous spectrum of Aldebaran. So it's a spectral intensity on here, side, and wavelength here in nanometers. So to do a quick graph, you like about 1,000 down here. And then you've got it, and then the next question is, determine a value for the temperature of Aldebaran without using Stefan's law. And you're going to give your workings. Always important to give your workings. Right, so first of all, you need to do is find the peak temperature, so on here. You can either take, between a range of 700 nanometers and 750 is what they say is acceptable. So use up to you what you think when you judge the peak of the graph. So you need to use Fein's law for this. So Fein's law, you need to rearrange it for temperature. So Fein's law, and this would be over x here. So, and the Fein's constant here is times 10 to the minus 3. 10 to the minus 3 meter Kelvin. So you have. So I picked when I looked at the question, I picked 720 nanometers. So we have that. So it's 12.2 times 10 to the minus 9. And then from that you get 4,028 Kelvin. About. I got 4,027.78, so around 4,028. And they said they'll accept a range of 3,867 to about 4,140. Okay, so the next question I was just explaining what a black body is. So they give you the actual to do it. So agreement between the temperatures found in A. So using Stefan's law, and B. This would help confirm that Aldebaran is an emitting black body. So they just ask, what is a black body? And you will be guaranteed you'll be asked this in every single black body spectrum question. And for 1 mark, then you get it's just a black body absorbs all electromagnetic radiation falling on it. They'll accept all light falling on it, and also they also accept a black body emits more radiation per second or at every wavelength than any other body at the same temperature. But it does not accept, do not put this down, it is a perfect emitter. So, under our final one, this is just a simple just from what you've understood from the rest of the question, I want you to explain, so explain using the data in the question, why a red giant is an appropriate description of Aldebaran. So, think of both the words, why is it red and why is it a giant? First of all, your Tmax, your maximum wavelength, is at peaks at about 700 to 750 nanometers, which is a red wavelength. They'll also accept infrared if you put that down. And then, so you say the spectrum peaks at the red wavelength, and also you make note that the radius is much larger than the sun. So the radius and you write down then, you can write again down the radius is that much bigger than the sun. And that proves that it's a giant. So we have all the things we need in the question. And if you do all these things correctly, you'll get 4 marks. Thanks.